Hello and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through the first section of Chapter 1, the Introduction to Statistics. However, before I go any further into the introduction of statistics, I want to give you a quick introduction to these videos in general. The purpose of these pre-recorded video lectures is to foster remote learning at Salt Lake Community College. When learning through these video lectures, there's a few things that I suggest to keep in mind. First, if you have access to the lecture notes that I use in these videos, as you can see here, have them printed out and at the ready so you can take notes about the concepts by hand. If you just listen to the lecture and don't physically engage to at least some extent, then you will have a much harder time of retaining the information. It's all about active versus passive learning, and it is always better to be active. If you do not have the lecture notes or you cannot find them, please contact your instructor to get access to them. Secondly, one of the primary benefits to this style of remote learning is that you can pause the video or rewind at any point. Please take advantage of this if something is confusing at some point. This may be obvious, but I want to put it out there. Third, if I do not explain something to your understanding, remember that there are other resources available to you, first and foremost being your instructor. Do not hesitate to ask your instructor about something that is confusing or you have a hard time with. There are a plethora of other resources that you can have available to you, so make sure you do talk to your instructor about what you can use and what you have available. Fourth and lastly, after finishing the lecture, I then recommend trying your hand at the homework and or quiz associated with the section. Once you've got the material down, you want to be able to try it yourself. It is as if I explained to you how to drive a car in depth, and then you neglected to try it on your own. The information will not stick, and the same is true here. I can explain things all day, but ultimately, if you do not give it a try yourself, it will go to waste. This is especially important in Math 1040 at Salt Lake Community College, as there is a lot of homework to do, so don't get caught behind. With that in mind, those notes about how to approach these lectures, I'm going to dive into it. Here we're going to be talking about the first section of Chapter 1, the Introduction of Statistics. First, what statistics means in general. You'll see here that I have a bunch of definitions. If you see them in red, that means that's a primary definition that you're going to need to know. And that's basically how most of Chapter 1 is going to be here. We're going to have a lot of definitions that you're going to need to know because they will continue through the entire class. You'll hear us use these words a lot. First, just the definition of what statistics is. Statistics is usually split up into 4 sections: how to collect, how to organize, how to summarize, and how to analyze information so that conclusions can be drawn with a measure of confidence. We're going to go through each of these stages slowly in these chapters. First, we're going to talk about how to collect data in Chapter 1. Then we're going to talk about how to organize and summarize the data in Chapter 2. And then we're going, and 3 really. And we're going to talk about how to analyze that data, and starting really in Chapter 3 and beyond. So we are going to go through all of these sections. First, Chapter 1 is going to be talking about how to get the data. The different types of statistics we can either have descriptive or inferential statistics. Descriptive means that you organize and summarize collected data, whereas inferential means that you have methods that take sample results and extend it to the population. This is kind of more what we're going to do. Descriptive statistics is only so good because you only are describing a small section of information. Basically, you collect some data and you say, here's the data that I got, and you end it there. Inferential statistics is taking that extra leap. It's taking the data that you gathered and trying to make an inferential jump or an inferential leap to say this data can help describe another group of information, not just the people that I analyze, a larger group than that. So we're going to do a lot of inferential statistics. In statistics, there are 2 different groups that you can have. First, the main group, the group in question that we're usually trying to describe, that being the population. The population is the entire group of interest in a study. So when we gather information, we're trying to consider, who am I trying to describe? Whether we gather that full population or just a group of that, we're always trying to describe some full population. And the population doesn't necessarily have to be huge. Sometimes it is large, like the population in the United States or the population of the world. Sometimes the population is a lot more focused. Maybe it's the population of individuals who shop at Walmart. Maybe it's the population of my local community, something like that. Whatever it is, we always want to dictate what group am I overall talking about, and then usually gather a small section from that. Each person in that population is considered an individual, whether that is a person or an object. So it could be a person or an object. Maybe I'm not analyzing people, maybe I'm analyzing cacti in Arizona. Then an individual would be each individual cactus. Now, the population is usually a lot harder to analyze directly. Again, if we did something like the entire population of the United States, or even if I did the entire population of Utah. That's a rather large group, and it's very, very inefficient or impractical to try to actually gather information from every individual in that population. Because of that, what we're more often going to do, we're going to take this population, say this entire circle is my population, and what we're going to do is we're going to take a section of that. This section that we gather, this is going to be called a sample. A sample is a subset or a section of the population that's being studied. Basically, the section that we can gather and talk about. The question is going to be how we gather that sample. That's going to be the primary question in Chapter 1 in general. How do we gather that sample so it is an accurate depiction of the population? Because sometimes a sample can seem really good, it can seem pretty biased in a way. Which means the sample doesn't really accurately represent the population. So that's going to be our question. How do we do inferential statistics? So how do we gather a sample to describe a population? And how do we do it in a good way? When we do gather this information, any numbers or really any values that come from a sample, any summary values, so we're going to talk later about means, medians, we're going to talk about just maybe averages, modes. We're going to talk about a lot of different values. Anything that comes from a sample, we're going to call a statistic. And any summary of a population, we're going to call a parameter. There's a really nice way of remembering that. If you notice that sample starts with an S, and so does, whoop, not that one. Hold on, erase that. Sample starts with an S, and so does statistic. So that's a nice way to remember that. And same thing with parameter and population. So any value that's describing a statistic, or any value that's describing a sample, we call a statistic. Any value that's describing a population, we call a parameter. Now, the reason why we don't just say it's just a number or it's just a numerical summary, why we use different words to describe them, is because usually one of these is unknown. And the one that is unknown typically is the parameter here. So the parameter will typically say is an unknown value. The reason is because it's something describing a population. If I know maybe the average height of individuals in Utah, if I know that number, that's the parameter, then why am I doing any sampling? I already have that value. The point of sampling is to gather a small sample, maybe 30 or 40 individuals in Utah, find their average height, which would be a statistic value because it describes a small group, and try to make that jump and say, all right, well, my sample is a good representation of my parameter. That's the point of statistics, taking the values from a sample, trying to describe what the population might be. Okay, so a few more definitions here. And we're going to go through examples of each of these, so do not worry if you're a little bit confused at this point. Again, it's just the beginning. Variables. Variables are characteristics of individuals in a population, and variables can really be anything that describes the population. Variables could be height, weight, age, eye color, hair color, favorite type of fish. I don't know. These are all variables, something that does describe an individual in the population. We call them variables because they can inherently vary. The people can have differing heights, people can have differing eye colors. All these things can change. Or these are usually the things that we're either trying to study or we're trying to control. Now, variables have some subsections to them. Variables can either be qualitative, sometimes known as categorical, or they could be quantitative. The trick to understanding what these words mean is looking at the first part of each word. Quality or qualitative starts with qual or quality, which means it's talking about a quality of a value. Or if you call it categorical, it's talking about a category. So it's responses that are attributes or characteristics. These are things like eye color, or maybe car style or make, or maybe I don't know, brand if I'm talking about like potato chips or something like that. These are all things that are considered attributes or characteristics. Most importantly, they're typically considered non-numerical. When trying to determine if it's qualitative or categorical, look at the responses you would have from this. If I was looking for eye color, responses I would get would be like brown, blue, green, red, stuff like that. Car style would be like Ford, Mitsubishi, stuff like that. Brand would be Lay's and et cetera, et cetera. All these different types of things, and like the things that are given to me are values that are not typically numerical, or they're not treated as a numerical value. If they are numerical, then that means we have a quantity that we are working with, not a quality. Quantity. That means the responses are numerical measures. So this would be something like, say, height, weight, temperature, something like that. These are all things that would be considered numerical measures. When I look at height, I'm gonna get something like 5'10" or 6'2", or maybe I'm in centimeters. Maybe I get 180 centimeters or 196 centimeters. These are all numerical values. Same thing with weight and same thing with temperature. Now, there are going to be some weird exceptions to this, values that look numerical, but they're treated as qualitative, and we'll get to those in a bit. Now, quantitative can be split up into a couple different styles. They could be split up into either discrete or continuous. And that has to do with what the numbers, or how the numbers really act. If they're discrete, that's going to be the same word as countable. That's going to be the best word to think about with that. Um, finite is not necessarily the best thing to work with, not realistically. The best thing to work with is discrete is a countable number of values. And the best way to think about that is look at your hand. If you can count up all of the different possibilities by simply indicating each of them with your fingers, then that means it's a discrete value. For example, points scored in a basketball game. I could have 1, 2, 3, 4, 5, 6, 7, 8. I can count out all these by just pointing at my fingers. Theoretically, I could go really, really, really high, and I could go infinite, more or less. But I can count them. There's a logical way of counting up all the possibilities. You could also think about how much it costs to buy something, so money. If I'm talking about United States dollars, then I would either spend 1 cent, 2 cents, 3 cents, or you can count that as 0.01, 0.02, 0.03, 0.04. All of these are different values that I can have, and I can count up all these numbers. So those are considered countable. If they're not countable, they're called continuous. Continuous is a little bit harder to get around, but basically the three that I had listed up here for quantitative, height, weight, and temperature, these are all continuous variables. The best way to think about it, because it's supposed to represent that there's an infinite number of possible values, the best way to think about it is to take a possible number and then add more decimal places to that. If that still makes sense as a logical description, then it's probably continuous. For example, height. Say I did height in centimeters. Height in centimeters. So 180 centimeters, that makes sense. 180.5 centimeters, that makes sense. So I'll start writing out here. 180, 180.5, that makes sense. 180.52, that's still a height, that's just an amount. 180.521, that makes sense as a centimeter amount. 180.5217, that still makes sense as a centimeter amount. And you can continue this trend. I can keep adding decimals arbitrarily, and it still makes sense as a logical value. I can have height be this, or this, maybe if this isn't centimeters, maybe this is pounds. This makes sense as a pounds value. This could also make sense as a degree measure. So 180.5217 degrees. So that would be the way to think about continuous. You can also consider, some people like to do it in the way of take a number that you know works and keep cutting it in half. So keep dividing it by 2. If you get to a point that it no longer makes sense, it's probably discrete. If you can keep cutting in half and still makes logical sense, at least to some point, we call it continuous. Or you could just easily say not countable. If I'm trying to count up all temperature values, yeah, on a thermostat, it tends to just say 57 or 58 degrees. It's not necessarily going to say 57.12483 degrees, but that's still a logical temperature value, whether I'm talking about Fahrenheit, Celsius, Kelvin, whatever. So just think about if it makes logical sense. All right. Now, that's a lot of terminology. Now, what we're going to do is show some examples of these to help you understand what each of these really mean in context. First exercise here, we're going to determine if these are going to be considered statistics or parameters. So really the question then is, if this is a statistic or a parameter, is this a sample that I have, which would mean that the value described is a statistic, or is this a population that I have in which the value described is a parameter? So that's really the question that I'm looking for here. First, in a study of all 2,223 passengers aboard the Titanic, it is found that 706 survived when it sank. So our value described here is 706 out of the 2,223 passengers. That is the value that's described. That is the characteristic that is given. Now, to describe whether this is a sample or proportion, I'm going to look at context within the sentence. The main word that I see here is kind of small, is the word all. Since it says that it is the study of all passengers aboard the Titanic, that means I'm describing every single individual aboard the Titanic. That means that this is a population that's being described. Therefore, number 1 is describing a parameter. They'll put in blue, at least for a little bit of difference. So number 1 is a parameter. I'll also put it over here, I guess. So parameter. I'll use S for statistic. So that's what we're looking for. We're looking for context within the statement. Not necessarily just the number itself. 706 out of 2,223 could have been a statistic, but because it said all, we know we're talking about a population. All right, number 2. A recent survey of a sample of MBAs reported that the average salary for an MBA is more than $82,000. This one's a little bit more on the nose. Again, the value that's given is the $82,000, but we want to see if that's a statistic or a parameter. We look around this statement, we see a recent survey of a sample of MBAs. We see the word sample, that makes it pretty obvious that we are working with a statistic. So this is a statistic value. I will say, though, that there's another word that helps with that, the word survey. This is kind of an innocuous one. Survey typically will imply that this is a sample. If you are doing a survey, then that doesn't usually mean that you are describing the entire population. If you are describing the entire population, that usually means you're talking about what is called a census. So, different things. Usually survey will describe a sample anyway. With that in mind, with a couple examples, I recommend pausing and trying 3, 4, 5 on your own and seeing how you do. On pause and check your answers here. For number 3, starting salaries for all 667 MBA graduates from the University of Chicago Graduate School of Business increased 8.5% from the previous year. So the 8.5% is the value that we're trying to describe, or really even the 667. But again, we have that same word we did in the first question. We have the word all right here. Whoop. We have the word all right here, which means that we're describing every single graduate from the University of Chicago Graduate School of Business. Therefore, this is yet again a parameter. Last two. In a recent survey of a Salt Lake Community College students, and I probably don't even need to keep describing after that point. You might have already seen the word there, in a recent survey. Since I see the word survey, that means I'm talking yet again about a sample. And lastly, in a recent survey of 457 attendees of Jumanji, 402 would recommend the movie. Well, 402 out of 457, since that was describing a survey yet again, that means we're talking about a sample. So notice that when I was describing each of these and trying to determine if it's a statistic or a parameter, I didn't even care what the number was. I cared about the context of that number. So I was always trying to look for the words like all, survey, sample, stuff like that. So context to try to figure out what I'm describing. All right, some more examples describing some other topics from the first section. Are they following a discrete or continuous data set? So remember that the word you're looking for with discrete, it really means countable. And continuous means infinite. So there's a countable amount of possibilities, or there's an infinite amount of possibilities. Now, I don't like the word infinite as much because technically things can be countable and also infinite, but it's really trying to see if it's countable or not. So let's look at these. I'm going to start from the first one down. Okay. In a survey of adult Americans, so since we said survey, that means we know it's a sample, but that's not really relevant here. It is found that 39% of them have guns in their homes. So 39% is the variable that we have, the percentage of individuals that have guns in their homes. And we're trying to determine if that is a discrete or continuous data set. Well, the value reported is a percentage. That's the important thing to keep in mind. Typically, a percentage can be anything. 39% is what is reported here, but I very well could have had 39.5%. And that would still make sense as a percentage value. Or maybe I had 39.52%. That still makes sense as a percentage value. Or maybe I had 39.527%. That still makes sense as a percentage value. So, because I can keep slapping on decimals onto this percentage value and it still makes sense, I would typically consider this as a continuous data set. So I'm going to use C for continuous and D for discrete. This one I would say is continuous. Now, some would argue that, say that, well, wait, you can't have a decimal amount of Americans. However, the thing to keep in mind is that this is a percentage value. Since the value reported is a percentage, I'm not really asking for how many whole Americans have guns in their homes. I'm asking for what percentage of them. And percentages can come out to be just about anything. Anything between 0 and 100 anyway. So that one is continuous. That one's a little bit contentious, but percentages are almost always considered continuous. Now, if it said something like the percentage rounded to a whole number, then it would be countable because then they could only have like 39 or 40 or 41%. But we don't have any of that indication here. All right, so that one's kind of contentious. The other ones should be a lot easier. The number of heads obtained after flipping a coin 5 times. All right, well, the possibilities of that, I could have 0 heads. 1, 2, 3, 4, 5. These are all the different possibilities I can have. I can easily count that by just pointing at my fingers. So just 1, 2, 3, 4, 5. I can count all of those really easily. That means since it is countable, it is likewise considered discrete. Okay. Now, note that it didn't have to end at 5. Even if I said the number of heads obtained after flipping a coin and I stopped right there, I would still consider this discrete. Because the number of heads obtained, I could have 5, 6, 7, 8, 9, 10, 11. I can still count all these out logically. There's a logical process to get them all counted by just going up by 1 every time. So it would always be considered discrete. All right, the distance Tiger Woods can drive a golf ball. All right, so say this is in yards or meters, either one. Maybe I say it's 480 meters. I'm just coming up with a number. 480 meters seems logical, and I could also say 481 meters or 482. Or I could just keep slapping decimals onto that. 480.2 meters. That's still just a distance. 480.21 meters. 480.218 meters. These are all just distance measures. I can keep doing this and keep adding decimals, so therefore we would consider this a continuous data set. Next, points scored in a basketball game. I already talked about this one. You could have, well, technically 0 points. 1, 2, 3, 4. These are all points in a basketball game. Typically, they go up to like 100, 101. They go pretty high. But no matter what, I can still count all these values pretty logically. So therefore, we would likewise consider this discrete. Fifth, volume of water lost each day. You may sense a pattern here, at least for a little bit. Volume of water acts just like distance. So volume and distance work in just about the same way. I can have decimal amounts of water. Maybe if I have 2 gallons or 2.1 gallons or 2.13 gallons, these are all logical values. We would still consider that continuous. I can continuously add decimals. It still makes sense. Now, length of a song, that one may be a little contentious. I would still say that this is, well, I would still say that this one is continuous. Reason being, if I'm considering length of a song as a number of seconds or even minutes, maybe I have 4-minute song or 4.2 minutes or 4.23 minutes or 4.239 minutes. These all still make sense. So I'd still consider it continuous. Now, if I had somebody tell me length of a song as it is listed on my iPod or as it is listed on YouTube, something like that, where it is limited to being a number of minutes and a number of seconds, then I may say it's discrete. Because then I would say, okay, well, you could have 4 minutes and 30 seconds, or 4 minutes and 31 seconds, or 4 minutes and 32 seconds, 4 minutes and 33 seconds. These are all countable. If I was listing it like this, as it is on a YouTube video or on my iPod or something, then I would say that's discrete. Because I can count them all logically. It would take a while to get to all possibilities, but I can still do it. Alright, last one. Number of words in a song. Okay, well, you can have 0 words, 1 word, 2 word, 3 word. I can count all these. There's no decimal versions of words, at least to my knowledge. So we would consider that discrete. Okay, so just try to consider if you can continuously add decimals, it's continuous. If you can't, if you can just count all of them, we're going to consider it discrete. All right, we have, I think, 3 more exercises. Yeah, we have 3 more exercises here to go through some of those terminologies, or terms that we had earlier. Classify the variable as qualitative or quantitative. So qualitative versus quantitative. Remember that we're looking at the root of the word there. We're looking at quality versus quantity. So we're going to see if the values given would be a quality measure or a quantity measure, as in like a numerical one. Okay, so these ones tend to be a lot easier. Gender, we're going to have things like male, female, some would say non-binary, etc. These are all things that we would consider as genders. These are not numerical measures, so we would consider these qualitative. For the purpose of this, I'm going to use L for qualitative and N for quantitative. So for gender, we'd say it's qualitative. Temperature, we had temperature before. You can have like 84 degrees Fahrenheit, or you can have 77 degrees Celsius, or you could have, if you know what Kelvin is, you could have 104 Kelvin. These are all different temperature values. They're all numerical in measure, though. So we're going to say that this is a quantitative measure. Nation of origin, we could say the United States, we could say Canada, we could say France, etc. These are all names of things, and they're treated as names, so we're going to say this is a qualitative measure. Number of siblings, you could have 0, 1, 2, 3, so this is definitely numerical, so quantitative. Number of days worked, okay, that's again a quantity. You could either work 0 days in a month, 1 day, 2 days, 3 days, 4 days, maybe even 5.3 days if you consider hours worked or something. Either way, these are still numerical in measure. You can notice a lot of these are pretty easy. The grams of carbohydrates in a donut, I don't know, 200 grams, 201 grams, I'm just coming up with numbers, 202 grams, maybe even as a decimal, 214.73 grams, I don't know. These are still just numerical measures, so yet again, quantitative. Big hint is the word number in the previous ones. That definitely means it's going to be quantitative. These next few, though, a little bit tricky. Phone number, okay, well, you can have like 555 1245, I don't know, just a random number. 555 9876, etc. These are examples of phone numbers. I'm hoping these are fake. These are examples of phone numbers. But even though they look like numbers, they aren't really treated as such. Not in the same way, anyway. With the numbers that we had in the past, if I add them together, for example, they still make a logical value. If I add 2 plus 3 siblings together, I get 5 siblings. Still makes sense. Number of days worked, if I add 3 plus 4 together, I get 7. Still makes sense. I can add grams of carbohydrates in a donut, like if you eat 2 donuts, then it's just a number of grams. It doesn't really make sense to add phone numbers together. So that's kind of a good way of checking if a number really is quantitative. Here, does not make sense to add 2 people's phone numbers together and get a higher phone number, I guess. That doesn't really make any sense to do that. These phone numbers are really a description of how to get in contact with you. Therefore, it is a qualitative measure. So, not all numbers are quantitative. Depends on how the number is treated. However, if we look at value of a house is in dollars typically, so maybe $35,000 or $140,000. Likewise, I can add these together, get $175,000. It still is just an amount. Still works like a normal number. It is quantitative. But zip code is another one of the weird ones. A zip code would be like 84123 12345 44186. I don't know, these are just random zip codes. These are all zip codes, and what they describe is where you live, since they're describing something. Doesn't, again, make sense to add 2 people's zip codes together, particularly if I added this first zip code and the last zip code I have listed, this makes a zip code that would actually be 6 letters or 6 characters long, which isn't a real thing, not in the United States anyway. So a zip code, since it is likewise describing where you live, like a phone number was describing how to get in contact with you, a zip code would be considered a qualitative measure. Zip codes and phone numbers are usually the go-to as an exception to show that numerical values or things that look numerical can be qualitative. I've also had students in the past bring up examples like jersey numbers. Jersey numbers just describe usually, maybe if you consider old baseball teams, jersey numbers typically described where a person batted in order or how long they have been there. It's usually what jersey numbers used to be. And they don't really make sense to just add two people's jerseys together to make a higher jersey. It's just a description of who that person is or what their number is on the team, something like that. So jersey numbers could also be considered qualitative. There are other exceptions like that. Most of the time, if it's a number, it's quantitative, but you do need to be careful of these weird cases. Okay, so that's an example, qualitative versus quantitative. All right, got another example here. The following information relates to the 2011 model year product line of BMW automobiles. Identify the individuals in the study, the variables, and if the data is qualitative, quantitative, continuous, or discrete. All right, so looking at this table here, we're looking at the 2011 model year product, and we have the models listed here. These models are your individuals. So the models that we have listed here are the individuals. So the 3 series, the 5 series, the 6 series, and each of those models have some variables that describe them. So these variables here are the things that describe them. The body style, so I'll say BS, body style, weight, and number of seats. These are all things that describe the model. The body style of the model, the weight of the model, the number of seats of that model. So these are all the variables that we have. Now working through these, the body style, well, looking at even the values given, the body style are like coupe, sedan, convertible. These are all descriptive measures. These are not numbers, these are qualities. So we would say that this is a qualitative measure. Weight, looking at the numbers here, 3362, 4056, 4277. These are all numerical measures, so quantitative. And same thing for the number of seats. Number of seats even has the word number in it, so you should know it's quantitative. Now, to determine if it's discrete or continuous, I'm actually going to start from the bottom up this time, so I'm going to start off with number of seats. Number of seats, well, you can have 0 seats, 1 seat, 2 seats, 3 seats, 4 seats. These are all possible number of seats. I can count them logically. It does not make sense to have like 7.48 seats. That doesn't make sense. So number of seats would be considered discrete. Now, weight is an interesting one. Weight, looking at the numbers here, we have stuff like 3362, 4056. These all look like whole numbers, which usually implies it's discrete. However, even though the numbers reported there are rounded or they're in whole numbers, it doesn't mean that something like 4,172.86 pounds, if it's in pounds, doesn't make sense. This is fine. It doesn't mean that this doesn't make sense. This could very well be a weight for a given car. Weight, just like height, volume, temperature, are typically considered as continuous variables because you can keep continuously adding decimals and it still makes sense. Okay. Last one. Body style, we have like coupe, sedan, convertible, etc. So these ones we would not consider continuous because we can't add decimals to these. We can't have like coupe 0.125. That's not a thing. It's also not discrete because they're not countable numerical measures. They're not numerical at all. So, for the question of discrete versus continuous, the answer is neither. Because discrete or continuous only describes quantitative measures. But because body style is qualitative, it is neither discrete nor continuous. Okay. Last example here, and then I want to talk about one more thing before we end. Smoker's IQ. A study was conducted in which 20,211 18-year-old recruits were given an exam to measure IQ. In addition, the recruits were asked to disclose their smoking status. An individual was considered a smoker if he smoked at least one cigarette per day. The goal of the study was to determine whether adolescents aged 18 to 21 who smoked have a lower IQ than non-smokers. It was found that the average IQ of the smokers was 94, while the average IQ of non-smokers was 101. The researchers concluded that lower IQ individuals are more likely to choose to smoke, not that smoking makes people less intelligent. Okay. Um, so what we're going to look at here, this is basically a description of an entire study that was done, and this is maybe something you would see in a news article. And we're going to be able to break this down, at least to the extent that we have right now. First, what is the population being studied? All right. Well, usually a good way of looking at what the population is trying to analyze what the sample was. That's usually one of the best ways to determine what I'm trying to describe here. All right. So what we have here, it says that they looked at 20,211 18-year-old recruits, and that's the sample that they gathered. That usually means that that's also the population. The population is 18-year-old recruits. However, later on in the description, it says very clearly who they wanted to describe. The goal of the study was to determine whether adolescents aged 18 to 21 who smoke have a lower IQ than non-smokers. That means the people that they were trying to describe were adolescents aged 18 to 21. So that's going to be the population I describe here. The adolescents aged 18 to 21. 18 to 21. That would be the population being studied. That means that the sample being the 20,211 18-year-old recruits, is not really that great if you really think about it. The sample here being the 20,211 18-year-old recruits. That's not really a good sample to describe the population, at least in my mind. If the population was trying to be all adolescents aged 18 to 21, why did they study only 18-year-old recruits? That means that they missed all individuals aged 19, 20, or 21. Yeah, the sample is really large, but that's not necessarily the best thing either. We'll talk about later on in statistics in general that sometimes large samples can muddle the results of the study. Anyway, so that's the population of the sample. The descriptive statistics, these are the values that were reported from the sample. So that's what the statistics mean here. It was found that the average IQ of smokers was 94. So that's my first descriptive statistic, is 94. While the average IQ of non-smokers was 101. So those are my two descriptive statistics. We have 94 IQ for smokers and 101 IQ for non-smokers. Those are the statistics that describe the sample that was gathered. All right, so at that point, we're just kind of breaking down based on things that we have. I do want to make one note, though, before I end this video. And the note I want to make are a couple terms that are left off of these notes, but will sometimes show up on your homework, depending on your homework set. What I want to talk about are the different measurement scales. Again, these are a small thing, but sometimes you see them in the homework. The different measurement scales, there are 4, so I'll put them over here. You have nominal, you have ordinal, interval, and you also have ratio. Nominal means that the level of measurement is just in name only, that there is no difference between them. An example of this is things like eye color. You're trying to see if there's a level of difference between the two, or if there is an inherent order between them. When I'm talking about eye color, I get colors like brown, blue, green, red. One color is not considered better than the other inherently. So there is no inherent order to them. They're just different names, which is what nominal means. Ordinal means that you have an inherent order between the measures, and both of these being qualitative. An example of this would be like medals in the Olympics. This would be typically considered ordinal because gold is better than silver, silver is better than bronze. Even though gold, silver, and bronze are not numerical, there is an inherent order between them. Or if you look at grades, grades are usually considered ordinal as well. A is better than B, B is better than C, etc., etc. So those would be considered ordinal. There is an inherent order or hierarchy between the variables. Interval versus ratio are how we distinguish different quantitative measures. And the difference between interval and ordinal, the main thing you want to think about between them is, what does 0 mean? If 0 doesn't have its inherent meaning, it's going to be called interval. And that's kind of weird to think about. Like, what do I mean that 0 doesn't hold its meaning? Well, 0 as a number is supposed to mean nothing, right? If I look into a field and I say that there are 0 trees, that means that there are no trees there. If there is a weight of 0, that means that there is nothing there. There's no weight. However, there are a very few amounts of variables that are considered interval, where 0 doesn't mean nothing. The biggest example of interval is temperature. At least Celsius and Fahrenheit. 0 degrees Fahrenheit or 0 degrees Celsius does not mean that there is no temperature. There is still an amount of temperature there. It's just very cold, is what it is. And we can have numbers below 0 that make sense. -5 degrees Celsius, -5 degrees Fahrenheit. These still make sense as temperature values. 0 doesn't mean that there's no temperature. It's just a different amount. So temperature is considered an interval variable. Everything else where 0 makes sense, we call ratio. So weight, height, most numerical measures are ratio. If you have trouble trying to consider which one is which between interval and ratio, if you look at the last letter of ratio, it is a O or a 0, indicating that 0 makes sense because it's part of the word. So that's a way you can remember which one 0 is supposed to be logical for. It's supposed to be logical for ratio. It doesn't mean 0. It doesn't really mean what 0 means for interval. So that's just a small topic. I want to at least quickly address it in case you do see those questions. But with that in mind, like I said at the beginning of the video, since you have finished this, I highly recommend going and trying your hand at the homework associated with this section before you move on into section 1.2. But with that said, I hope you have a great day.